Hello everybody, this is Luboš Pirkl from CFD Support. Welcome to the webinar, which today we called Tips and Tricks in TCFD and ParaView. And we believe that ParaView is extremely powerful tool. So this time and today we would like in this webinar focus on ParaView, which is great tool, especially for CFD post-processing. And we believe it brings a lot of value to its users because it's open source and it's freely available to everybody. And yeah, we would like to show you how we work with it. We would like to show you our approach to it, and really we would like to give you some useful tips and tricks what you can do. Well, the webinar is being recorded, and its recording will be made available on our YouTube channel. And I believe this time all the techniques work well, and if not, feel free to contact us in the future, and we will gladly answer all your questions and comments. We are here for you. It's our job and also our pleasure. So feel free to contact us anytime. Okay, I will start with the introduction of the webinar speakers. So this is me. My name is Luboš Pirkl. I am co-founder of CFD Support, and my current job here at CFD Support is telling the world about CFD Support. And today I'm here with my colleague Radek Maca. Hello, Radek.
Hello, Luboš, and hello to everybody.
Great to hear you. Are you ready for the webinar today?
Yes, I'm ready, and please continue.
Okay. So thank you. So Radek is our head engineer and senior developer here at CFD Support, and in today's webinar he will show you live what he will show you miracles he does in ParaView. Here's the agenda of the webinar for those who stay. There will be introduction, which I will show. I will say what we do, what's TCFD, and a little bit about what's ParaView. I will give you the introduction. After that, Radek will come here to this computer and will show you what he has prepared for you in ParaView. You can be looking forward for a great presentation of tips and tricks in TCFD and in standard ParaView. We will do our best to distinguish between what we did and what standard ParaView are available freely for everybody. And at the end of the webinar, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions. There is a special window where you can ask your questions, and we will gladly answer all your questions, or those questions we will be available to answer in time. So yeah, Q&A at the end. So I will start with a very short introduction of CFD Support. So CFD Support is a Czech company. We are located in Prague, Czech Republic, and we are dealing with computational fluid dynamics in general. Yeah, we do all the engineering projects on CFD across the field. We are focused on open sources, especially on OpenFOAM. So we do a little bit of OpenFOAM training. We still do quite a lot of OpenFOAM technical support and custom code development. And in the last years, our flagship product and our core business is developing, maintaining, updating, and delivering TCFD, which is a workflow for computational fluid dynamics. Right in the beginning, I would like to say that ParaView is open source project developed by an American company called Kitware. So Kitware is the producer and maintainer of ParaView. They develop it. You can find all the information on these websites. So they're official. There you can find all the information. And I will say now what we do. So here at CFD Support, we develop the code TCFD, which is a comprehensive CFD software. We have successfully merged the benefits of the open sources, which is it's open source, it's flexible, it's unlimited, with the benefits of commercial codes, which is it's professionally maintained, it's regularly updated, it's tested, it's validated, and it has graphical interface, and it's ready for the industry. TCFD is always focused. We never say it's general purpose code. It's focused. So turbomachinery or TCFD core business has always been turbomachinery simulations like pumps, fans, turbines, or compressors, or hydro turbines, for example, or wind turbines. And what had worked so well in turbomachinery field, we have later extended to car external aerodynamics, or for the aircraft, or for the internal aero, for various valves and manifolds, and etc. And also we have extended TCFD to be able to simulate hydrodynamics of, for example, ship hulls and propellers. It's TCFD core business. What's important, TCFD always from the beginning is created to keep its modular character. So it's developed to be as compatible as possible with all other software available. It's created to fit any existing workflow. It has strong integration ability to really work in parallel or together with other software, with various either commercial codes or with in-house codes or with all of them. It's always focused. It's ready for unlimited simulations. It's ready for optimization. It's automated, and we believe it's technology of the future. It's focused and it's unlimited. So a very important capability of TCFD. It's automated. It can be used on the basis of data in and data out. So the user can either just put the data to TCFD, TCFD does its job, and then the user just picks the results, or TCFD can be used as a fully sophisticated CFD code where all the options are open. So the beauty of TCFD is it's the user who decides how deep to dive into CFD or not at all, or use it as a black box. Okay, we have few benchmarks to show, so I will go very quickly here because there are PDF versions and studies of these studies, so they're available. So I'm not gonna go into details. I have few benchmarks to show for you. So for example, this one we have created together with our good client ZVVZ machinery. It's a benchmark of centrifugal fan, where we simulated a centrifugal fan where the fluid flow is actually pretty complicated, and the measurement is available for this centrifugal fan. So we made an extensive study of transient and also steady state simulation of this centrifugal fan, and you can see the result here, and also feel free to ask the details. I will continue. This is a similar case. We had another benchmark that's a little bit different because it was on compressor together with our client CZ, who develop compressors. This is radial compressor, so the flow is compressible, and again you can see the comparison with the measurement and other code. Again, a PDF of this study is available, so anybody who is interested in details can ask for it, and we will definitely provide it. Yeah, for any code, for any workflow, is extremely important to scale well or very well. So we did also parallel scaling benchmark on hydro turbine, where we refined the mesh many times, and for that we have used TCFD, and to show the parallel scaling ability of TCFD, and the results are really great, which you can see here. So if you double one time and if you double few times the resources, you still get the linear speed up and very high parallel efficiency. Again, detailed PDF is available about this study, so I will continue. Yeah, this is another example where the external aerodynamics of the aircraft. It's the aircraft with rotating impeller. So again, we were able to find actually it's Spitfire, which is the aircraft from the history, and we were able to find some data as they were measured 70 years ago, and we made a comparison of TCFD results, and then yeah, the agreement with the results was fantastic. I will continue. Yeah, this is the optimization study we did together with Cases, which is parametric CAT developed by German company Friendship Systems. Yeah, and yeah, because we have lost some time at the beginning of the webinar, I will go very quickly. Our vision for the, let's say, in 2 years, we would like to present TCFD, or we would like to develop our system in a way that we would like to present it much more to be a CAE platform rather than just a CFD code. So this is our vision. We would like in 2 years we would like to introduce a complete workflow where there will be the CAT system integrated with CFD and with finite element system. All of them will be based on open sources, and then they will be maintained by the master process, which is the work name right now, and also communicated with the database of the results and be able to write it and read it. So we have let's say for the future the horizontal development, which is adding new tools, new plugins, and adding complexity, and also we have vertical development, which is adding new applications, new capabilities, and high-tech methods to our workflow. Okay, yeah, I had a little story, but I'm not gonna tell it right now. I think it's the right time to let Radek doing his job.
And in this part of the webinar, I would like to show you some live examples of how to work with standard ParaView or with ParaView with TCFD plugins. So first of all, what is TCFD? So TCFD is a complex workflow for CFD simulation. So it includes OpenFOAM-based software. So it is based on OpenFOAM, and we have developed new solvers, boundary condition, post-processing tools, and many other features. Then we developed our own code written in C++, which is called CFD processor, which is basically the heart of the TCFD, which manages all the processes for the whole CFD workflow. And then, because we would like to make TCFD user-friendly, so we developed graphical user interface directly in ParaView via special filters, which can be used for managing the whole workflow from the setting the case up to the visualization. So we use ParaView, which is a great software. It is a multi-platform data analysis and visualization application. So the standard ParaView is used for data visualization and analysis. So it can be used for CFD setup, for mesh processing, and so on. So we take ParaView, which is a great tool for data visualization, and implemented the processing tools using the filters, which I will mention later on. So here at CFD Support, we develop special filters for managing the whole process, as well as we develop special filters for some turbo machinery post-processing stuff. As well as we developed a special ParaView launcher allowing working on remote desktops graphically, which is now automatically chosen if your computer has compatible drivers or not. Then If not, some software emulation is used, and this is needed for working on remote desktop. So now you can connect to your remote PC with TCFD on your cluster or anywhere else, and working with the graphical user interface. So just quickly repeat TCFD workflow. So first of all, we need to have some input geometry or input mesh if we would like to use external meshing tool, which is not the part of the TCFD workflow yet. And then it comes the CFD simulation setup, which is the starting point for TCFD. And you can choose two options. First is to use the graphical user interface, which is TCFD source. It's a special filter which can be enabled in ParaView, and then you have all the menus for setting the TCFD simulation. Or you can go directly to manually type or manually define the file configuration file for TCFD, which is not so user friendly. Then the processing part, basically the filter for managing the processing and all other tools is called TCFD Manager. So here you prepare the case, you prepare the mesh, run the simulation, generate results, basically generate HTML report, and you can directly, using TCFD Manager, show the results. So load the data into ParaView and then post-process or visualize the data in the standard ParaView, basically. So TCFD source and TCFD managers are filters developed here at CFD Support, implemented in ParaView. And the CFD processor, which manage all, so you can also run all the processes without graphical user interface and in so-called batch mode, so just in the command line. And quickly, what ParaView is. So ParaView is an open source multi-platform data analysis and visualization application. So it can be installed on both on Linux and Windows, and additionally on Macs as well. It provides visualizations to analyze data using qualitative and quantitative techniques. So basically, you can visualize the data, or you can also find some integral values and so on. So I will show you one example of it, how to evaluate, for example, some average values on a given plane, for example, or on given object in general. It offers data exploration both in 3D. I can see Luboš is here already. Some noise is in the background.
No.
So, and programmatically, so basically ParaView has also a batch mode using which you can create script which can automatically visualize your favorite visualization or any render view without graphical user interface. And originally ParaView was developed to analyze extremely large data sets. So it includes some parallel capabilities and server capabilities for evaluation extremely large data sets on big clusters. So I'm not going to show you how to use this, because for our CFD simulation, our memory on standard computers is okay to visualize one simulation on one CPU. ParaView is a big project itself, so it includes extensive guides, tutorials, and documentation. So you can find them on the ParaView web pages. So you can follow these links and really follow some guides to learn new features which can be done in ParaView. And some of these features I will show you within this webinar. So TCFD GUI is implemented in ParaView via the filters, and the current version is the newest version of ParaView, version 5.6.0. So let me just briefly show you the layout. So this is the layout when you're working with TCFD filters, and all of the parts are standard ParaView, and some of the parts are created by TCFD plugins, which you can see, for example, here there are several icons for TCFD plugins like the TCFD source, which holds the TCFD setup and the menus using which you can preset the whole simulation. Then standard render view, in which the TCFD source can show you the input geometries. The TCFD manager can show you meshes, reports, or residuals and quantity monitors during the simulation. And at the end, it can show you HTML report. Additionally, it shows you the ParaView output messages, so some warning messages if something happened. And also it shows you, because the TCFD source communicates with these output messages, so when your setup is not compatible with what is expected, then it will show you some warning message or error message that some part of the TCFD setup is not correctly set. And also you can see the direct output of the solvers of any processing tools which is run on the background within the TCFD simulation. So first part or first filter I would like to mention is this TCFD source, which basically holds the simulation. So I will open some example case. So I will take one of the tutorial cases. So this is the axial fan segment. So it's a geometry of the axial fan. So I think it's a good example to show you the simulation and some post-processing features live. So basically this is the layout for TCFD and ParaView when you open a preset case. So we can see here, so I will close this because I don't need it now. So this is the pipeline browser with a TCFD source, including the settings and the components, which is basically the input geometry here, right? So we can anytime, what can be visualized, then you can see the eye, which is open or closed. It means the data are visualized or not. And then the settings includes in the properties menu or properties window, it includes several menus using which you can preset the simulation. So this is basically this. Then you can open it, new TCFD source, by directly clicking the preset configuration file or clicking the icon on the desktop, or you can use this icon to create new TCFD source. But I suggest having just one TCFD source within one ParaView session, because then everything is clear. So this is the TCFD source. Then there is, as a part of TCFD source, the TCFD includes some automatically generated visualization like blade-to-blade views or meridional averages, which can be preset within the TCFD source. So which plane, which field to be visualized, and so on. So this can be done directly. And any other visualization can be done with the standard ParaView after the simulation. Then the TCFD manager. So anytime I am ready with the setup, I can activate this TCFD manager, which holds additional components. For example, it holds the mesh, it holds the report, it holds the graphs of quantity monitors. So for example, you can follow the efficiency during the simulation, or you can follow the residuals. So I will show you later how to work, how to manage, how to create new layout, for example, to have 4 plots to follow each quantity and so on. Okay, so this is TCFD manager. Then common things you can run or write the case. It means it writes what you have set in the TCFD source. You can run the meshing. You can generate each component separately. You can visualize it, check it, go back to the settings, change the parameters, go back to the TCFD manager, regenerate the mesh, and when you are satisfied, you can go for simulation. You can manage the simulation by skipping to next point, because For example, for simulating turbo machinery, you can simulate many operating points within the one simulation, so you can skip to the next point if you see convergence. Anytime you can abort calculation, or you can anytime quit the calculation and write the simulation, for example, to see what happened, to see immediate, or to see the actual visualization of your simulation. And at the end, you can generate the report, as well as you can show the results depending on your simulation, if going in steady state or in transient mode. Then new feature in 19.04 is that you can follow any quantity which is evaluated during the simulation. So you can create your own layout. I will show you within a few minutes, and at the end you can visualize HTML report, or you can visualize it directly in graphical user interface, or you can generate it and visualize it anytime during the simulation. And the results can be visualized directly with the TCFD manager. So you can click here to show results, and the data or the data from the simulation are automatically loaded into ParaView, or you can open ParaView, standard ParaView itself by clicking. There is, in each simulated case, there is a file case.foam, which can be directly opened, and ParaView load automatically this data. So now finally we are coming to the live example. So let's start really from the beginning. So what the TCFD source are, and how to play, for example, with the menus. And so I will go back here. So for example, in the settings part, you can click this advanced button to enable advanced options. New feature is that you can undock these menus. For example, some menus can be really large and wide because the data are there are a lot of STL. The names are pretty long, so you can anytime undock it by the clicking on the scroll button on your mouse, and you can extend it and play nicely. Here in the separate window, you can open any window you want, and after the closing it, you can go back in the standard setup. So this can be done easily here. Then, for example, if I go to the TCFD manager and run the simulation, so I will write the case and run the simulation. So you can anytime open, for example, new render view. So if you would like to open new window, you can split new window or close any window and open the new one. So for example, I will split this one. Then, okay, I will close these because I don't want to see them now. So I can create new render view, and in this render view, I can visualize what I want. For example, when the mesh will be finished, I can visualize the mesh in the separate window. Okay, for example, I can open another window, for example, one for the stutter component, let's say, second one for the rotor component. So here I will click, then I will click on the show. And of course here in the pipeline browser, because this pipeline browser is specific for each window. So here, for example, I can see that both components and mesh are visualized. So I don't want to see mesh here. So here's the components, and in this window I would like to see the mesh. Yeah, right. So here I can see the mesh. Oh, sorry. Then what I can see, for example, I would like to, okay, and now I can show everything. So this mesh component holds the whole, everything what you said here. And by right click, for example, I would like to hide this stutter block. So right click, I can click hide block, and I see here only the rotor part, and the same here. For example, I can open the mesh again and hide now here the rotor part to see just a stator part with the edges, for example. Now I can link the cameras by right click, so link camera, and now I need to click to the window which I would like to link. So now I have these two window linked. You can see it. The camera is adjusted in the both window. In the same way, I can link the camera with the upper render view, and I can now nicely change the camera position with all three windows. When I would like to unlink the camera, you need to go to the tools and manage plugins. Sorry, not manage plugins, but manage links. And here, okay, so I would like to, for example, unlink the camera between the render view 3 and render view 1. So this is this, so I will just remove it, close, and now this is separate window, and this is still linked with this. Yeah, so in this way you can create as many render views as you want and link the camera as you want. So this was the render views. Now the simulation is running, so I can, for example, show you how to visualize the plots. So here I can create the new layout for the visualization. So by clicking the plus here, I can create new layout. And now I would like to see the quantity monitor charts and the residuals charts. So to do that, there is an item line chart view. So I will open it. And now I would like to see, for example, residuals. So I will click on the eye on the residuals, and now I can see the residuals. Additionally, for example, I would like to see some quantity during the simulation. So I will open the quantity monitor. Now I can go a little bit down here, and okay, I will uncheck everything and check, for example, just the efficiency and the average efficiency. Okay, but the scale is not good for me, so I can go down in this menu and find left axis custom range, and yeah, the efficiency is always between 0, should be always between 0 and 1, so I can scale this, or I can create a custom range. Okay, efficiency is fine, but I would like to see, oh, not render view, sorry. I would like to see, for example, the torques as well. So I go for new line chart view, again visualize quantity monitor, and go for torques, for example. Where is it? So average and instant torque values, and again I can adjust the range for the y-axis. So this is right axis, sorry. So where is the left axis? Sorry, I'm too low. Yeah, here. So what is the value? Okay, let's say 30 and 40. Okay, so now, for example, now I can see that the simulation is converged because everything is pretty steady. So I can click skip to the next point, and you can see that, yeah, we are almost at the end. And now the second point is simulated. So in this way, you can create as many windows as you want with plots or render views and so on. So there is no limitation. So I will just go back to the presentation just to check my notes. So TCFD source menu, TCFD manager, basic layout, render views. We created new render view. We link the camera, interactive block hiding. Yeah, so we can use right click to hide what you want or show what you want. Line chart views, yeah, and at the end HTML report views. Okay, so I will show you this. So anytime during the simulation, I can generate a report. So I suggest generating just a light report during the simulation because it generates the data like residuals, flow rates, and so which are important. For example, most important to see if your simulation is converging. But yeah, now you can see it directly here, but you can also see the information about the mesh, how many cells are there, and many other stuff. And to see the report, when you close the window for report, there is a item HTML view. So here, and then when the report is generated, you can click next to the report to visualize the report. And whenever the report is generated, and that directly appears here, and you can follow it directly here. If you have, for example, transient simulation, so you have both steady state and transient reports, so you can generate new layout, create new HTML view, and show the report for the transient. So in case of transient simulation, you will see here also, you can pick here the transient report, so we have only one. Or if you create more efficiency probes, you can visualize them here. All right, so now I think it's time to show some visualization, right? Yeah, so we are here. So I will, let's say I am satisfied with the simulation. So I have, our first point is already simulated, and let's say the point 2, let's say it's pretty converged, and I don't want to see other points, so I can click quit calculation plus write. So I will have the result from the first point and the result from the second point at this quitting iterations. So now I will be able to visualize the results for these 2 points. So now the simulation is quitted, and if you use this option, then you can also generate a full report, or in case you click run all button, then the full report is generated automatically at the end of the simulation. So I will create new layout, render view. So to visualize the results, we have 2 options. First option is to directly use TCFD Manager, and at the end we have here show results. So I can click on it. Then in the pipeline browser you will see the item case.foam, which holds the data of your simulation. So here we have our geometry with, for example, a static pressure field visualized on the surface. So what I would like to show you, okay, there are, what is the cell data versus point data? So as you can, sometimes it's a bit strange that there are always two velocities, 2 pressures, so 2 quantities, one with the point icon and second with the box icon. So the box icons shows you really the values in the cell centers. So each cell is colored by the value inside the cell, which the simulation gives you. Yeah, so TCFD and the OpenFOAM on which it is based uses the cell-centered scheme, so any quantity is stored in the cell center. So this is really what you get from the simulation. And because ParaView needs some point data to, for example, generate streamlines and so on, so it automatically generates the point data, which is just the interpolation from the cell centers to the point or to the vertices of each cell. So basically, it's just the, let's say, bilinear or trilinear interpolation. So it seems that the data are much more finer than it is in reality because of just the interpolation. Yeah. So one visualization aspect is that the point field looks much more fine than the cell fields, but it's just the interpolation. It's nothing with the accuracy of the results, of course. So this is the cell data and point data. Okay, extract block filter. So here we have the the whole geometry, which usually consists of several components. And now I would like to see just one component. Yeah, I would like to analyze just the rotor part, for example. So for this purpose, I need to apply a special filter which can extract each part of the of my whole geometry. And to have this option, I need to click here. So if you denote this case, the foam, you need to click or check these read zones. So it automatically reads all the zones in the mesh. And basically you can understand it as one component is one zone. So we can apply it. Okay, so now we have the zones as well. And now we can apply a filter which is called extract block, which is this one. And now you have available all the zones inside. So there are some reference frames which you set rotating or non-rotating, and in the same way the zones which are named by your defined component name. So I would like to visualize just the impeller zone, for example. So when I click it, then I can see just this component. Okay. So this, okay, I have it, and now I don't see. There is also the option, because now we have the component without, or we have no. If I click this extract block, I can name it as impeller, let's say, zone, and I have no data here. And when I check that, there was an option to copy also the data to your extracted part, which is not here, which is okay. Maybe I don't know why. So I will close and I'll load it again. Maybe I open it too early. So I will go back here and show results again. Yeah. Okay. So here are read zones. Okay. So that's strange. That's strange because there is no this option. Okay. Let me open new ParaView again. So here is my simulation. And the second option, how to load the data, is directly click this case.foam file. And now, yeah, okay, now it works. I don't know why. So if you click the read zone, you should see also the copy data to cell zone. So you need to check that as well to extract each part with the data as well. So I will repeat the process. So I will load the data. Okay, and now I will apply the extract block, or I can go to the recent, so it will show you your recently used filters. So extract block, and I would like to see just the impeller part. Okay, that's perfect. So now I have only impeller with the data, yeah, so I can see pressure fields, velocity fields, whatever I want. And for example, now I would like to make, let's say, some slice and to see the 3D blade-to-blade view, for example. So first of all, I would like to copy the segment to see at least 3 segments, for example. So there are 2 options. First option, which is not so clever, is to use, there is some transform filter, which can transform you anything what you say. So you can define translation, rotation, or scale. So I think it has 20 blades or 18, maybe 18 blades. So the rotating angle is 20 to get the neighbor, if I remember correctly. And when I visualize also the extract block, I can see, okay, so not 20. So there are 20 blades, so the transformation will be 18. degrees. Okay, so you can do it in this way, but you need to apply another transformation. So this is not so clever, but for general transformation, one transformation, you can use this filter. But there is also a filter which is called angular periodic filter, which is what we need here. So rotation angle, so basically if you divide 360 by the number of blades, you will get this rotation angle, which was 18, right? The axis of rotation is Z in our case, center is 0, 0, 0. And if I apply here, it will create a full wheel geometry, but I don't want to see, so iteration boundary is maximum, so as many segment or all the segments which are needed to build the full wheel. Or we can say manual mode and number of periods just 3. Yeah, this is what I need. So I will click and it will automatically copy the segments to see all three parts. Yeah, so this is the periodic filter. Let me just check what I would like to show you. So full wheel geometry from a segment. So this was this angular periodic filter. Then we can apply also meridional average and turbo unwrap, which is our filters for turbo machinery post-processing. Okay, I will show you this glyphs now and surface glyphs, for example. So vector visualization. So what you can apply anytime is for visualization for vector visualization. So we can use this glyph filter. You will set what field would like to visualize. So I would like to go for relative velocity on the rotor part. You can scale it by any field you have, and here are some other parameters how to scale or how many vectors and what the distribution of the vectors should be. So I will apply the standard mode. So then, all right. So this was, it's not a good day. Okay, so ParaView, tell me something that, all right. It's not a good day for webinar, it seems. So ParaView crashes now, maybe because some OpenGL driver problems. Okay, so let's do it again quickly. So I just applied the vector on the source geometry, which was this 3 segments. So quickly I will repeat it just with one blade. All right, so okay, I will show you how to do it on the both components. So click on the glyph filter. I would like to go for the relative velocity, and now I can visualize the. Okay, I can't. All right.
I think it's okay. You can just continue with other agenda. So that's okay.
No, I think okay. So I have many more to show. So give me just last try for this. So I don't know what happened. Nevertheless, okay. So I will just try to show, for example, the second thing I would like to show you is to generate vector fields on a given plane or slice. So you can create a slice, any shape. So you can create plane, box, sphere, or cylinder. So I will take the cylinder for, let's say, to have a radial slice. So I will just adjust the cylinder with our geometry. So the center or the rotation axis is in Z direction, and point on the axis is the point 0, 0, 0, of course, and let's say the radius I will take something like this because I think shroud is at the coordinate 0.2. All right, so we have a slice. So now hope I will be able to create the glyphs. Hopefully, last try. Okay. Okay, so the the glyphs are not possible to visualize at this computer, but in the morning it worked well. All right, so not a good day for this. So let me show you another tools. Okay, so I will show you some fancy streamlines. Let's say I hope it will work. So I will open it again. Okay, internal field. All right. So I will generate a surface streamline just to see, because you need to create some seeds from which the streamlines will be generated. So you can anytime create or change the visibility. So I can, or the opacity of your geometry. So I will put something like this to see inside my geometry. Then I will apply stream tracer. There are two options how to define the streamlines based on the higher resolution lines. So basically the seeds for the streamlines are those cells intersected by the streamline. So if I apply it now, we will see, yeah, some streamlines, right, during going through this high resolution line and my geometry. Or I can create the point source. So it is basically a sphere with randomly distributed points, and the number of points you set here 100. So I will set, for example, 30. Okay, so this is absolute velocity, which doesn't make any sense to visualize on the rotor part. So we can directly go for the relative velocity here. So now nice, it looks better. So I can go, for example, for this, and to have, I don't want to see this source sphere, so we can uncheck it here. And to make it more fancy, you can apply a filter which is called tube. So I can apply tube on the stream tracer. Then you can see that these are more solid and looks more fancy. You can play with the radius, so we can make it thinner or thicker. Yeah, in this way you can visualize any field on them, and you can combine them. Yeah, you can create new stream tracer at any different place and combine it together with surface visualization or surface representation. So you can, for example, see a wireframe which makes very nice images. So you can really play with the colors, for example. So I can get solid to see the black wireframe with the streamlines and so on. Okay. So the last thing on this example, I would like to show you how to, for example, generate for example, average value, surface average, or mass flow rate average value on any slice you prefer. So let me make a slice. So I will make a slice through my domain. So let's say here, and not to be so much easy, so I will create this random slice somewhere in the middle at the interface between rotor and stator. Okay, so this is not, oh, maybe yes. Maybe it doesn't make any sense to make this slice, so I will move it, for example, just behind the rotor. Yeah, this will be nicer. So I would like to, for example, evaluate total pressure at this plane, at this random plane. So to do that, there is a filter which is called integrate variables, and I will find it. So I is where integrate variables here. So I can apply the integrate variables, and what it does, it will take basically the value on the face on this slice multiplied by this multiplies this value by the area of the part of the slice and sum everything up. And then in this new window which appears in the cell data, so there are again point data and cell data, so you will go for the cell data and you will see the total pressure value integrated, and to have the average you need to divide this number by the area which is somewhere here. Yeah, so this is the area of the slice, and this is basically all these values are sum of the value of the variable on each part of the slice multiplied by the local area of the slice. And then if you divide it by area, you will get the area average. If you would like to create the mass flow rate average, it is more complicated, because first you need to generate the mass flow on or the mass flow part on each part of the slice. So first of all, what we need to get the normals, because only the normal component of the velocity to your slice generates the mass flow, right, or volumetric flow. So first of all, you need to apply the filter which is called generate surface normals, which is here. So we can apply it. And I don't want to go for the glyphs, but when you are click on the glyphs, you will see nicely the normals which were generated. Okay, so I have normals, and now I can create the fields which will be averaged by the mass flow. So basically, I need to create a new field using the calculator. So calculator is a nice option because you can create any field based on the values which are available. So you can create any new quantity. So I will take so generate surface. So I think, yeah, here we have the normals, right? So I can take normals. I can make a dot product with the absolute velocity, yeah, to have the normal component of the velocity. And if I have, for example, compressible case, I can multiply it by the density to have a mass flow rate. Now this will be volumetric flow rate, right? So let's say I will name it as phi. So this will generate new field. And the second thing, I need to create the averaged or the mass flow averaged quantity. So if I would like to go for the total pressure mass flow average, so I will take the total pressure, which is here. I need to multiply it by my new field here, this one, and I can name it as p dot weighted, right, in this case. Okay, and now when I make an integration, so I go for recent, integrate variable, go for it, then I have here the values. So for example, I have the value of the weighted total pressure, but again, it is a sum of the mass flow rate times my variable, and summed over the slice. So I need to define by the mass flow rate, right, which I can read here. So if I define this value by this value, I basically get the total pressure mass flow averaged at any general slice. And in this way, I can create any averaging of any quantity on any slice or on any shape. Okay, so this was surface and flow rate averaging on the general plane. Okay, so I will skip our meridional average and turbo unware because we have shown it many times in previous webinars. So I will go for next examples. So now how to, for example, simple showcase how to make some animation and how to work with transient tutorials. So I will close this and I will take our radial blower 2D transient. So it's simple 2D geometry of radial blower, which can be run pretty fast in transient to show you real life. So I will open it in TCFD in ParaView and okay. So very simple geometry. Here I have steady state plus transient simulation. I have the time step corresponds to the 1 degree of revolution of the wheel. And what I need to think about when I would like to have some nice animation is that if you go for post-processing, there is a snapshot interval which gives you the option how often to save the data. Yeah, so here I set that every 2 degrees, so it means every 2 physical time steps, it saves me the data. Yeah, because if you count, for example, I think it's something like 50 blades. So one segment, for one segment, we have 7 degrees. So I would like to have at least 3 or 4 frames for one segment passage, yeah, to really see some animation. So you need to think about how many frames will mate 1 second of your video and so on, and if it should correspond to some speed up or yeah. So you need to think about it, how many snapshot intervals and how often to do. And of course, because it is really hungry for the space on your disk, so you should just save only your favorite variables. For example, I will go just for the velocity field here. Yeah, so when everything is set, so I can go for TCFD manager and generate quickly some visualizations, or basically first the result and then some visualizations. So I will run it. I just preset one iteration for steady state to really start directly the transient simulation. So now it's part of the steady state and then the transient simulation will run. So we will wait a bit. So just 1 minute to go. So maybe I can prepare. So what I'm going to show you, so setting the snapshot interval is important. Otherwise you can't generate any animation because you will have only the data at the end of the transient simulation. Then I will show you how to show the transient simulation, how the structure looks on the disk, how to run the animation, how to, for example, adding the time label, how to adjust the camera, how to save the animation, and for example, how to apply another filter to follow just the data in some range of its values, for example, as an example. Okay, so the simulation is done. So okay, I will close all these windows. I don't need them now. I would like to have just the render view. I will close. I don't want to see the mesh and components. And now I will go to see the results. But now I would like to go for transient. So each point is saved in the special place on the disk. And we have only 1 point simulated here in the transient first speed line and first point. Yeah, so I click on apply and I will show this. So this is the result. So automatically we can see that I've simulated just a quarter of the rotation, yeah, so just 90 degrees of rotation. And if you play the animation, which you can go here, you will see that something is moving. Right, then I can visualize, for example, yeah, I can go not for the last one. Yeah, because if you can see for the last time frame, so it is the end of the simulation, TCFD automatically saves all the data, but in intermediate steps, it saves me only what I set, and I set only the velocity field. Yeah, so and I will go for the related values. So this, let's say we have from the simulation, yeah, something is happening. Now how to save the animation, or maybe before I will do some additional things. You can also, for animation, it is important, for example, to adjust moving camera and moving views, which is more fancy, right? To show on YouTube. And to do that, you can enable the animation view, which I already have done. And so this is the animation view in which you can play with adjusting any parameter of the simulation in visibility and so on. But what I would like to show you is to adjust the camera. So you can go for the camera, and there are many options how to adjust. So to have the orbit or define a path along which the camera will go. And I like this interpolate camera because you will see how it works. So I will check this. I will add this option. Now, if I double click this bar, a new window will appear, and basically it's just the adjusting some, let's say, kind of linear adjustment of my views, which I define here. So for the first time and the last time, and of course you can add any intermediate steps. But for example, let's go for let's say the starting view will be this, right? So I can click the first point, use current, okay, and let's say this will be, okay, I will make it, let's say this will be my last view for the last frame. So use current, okay, and now I will check if, yeah, and you can see that the camera is adjusting between these two positions. Okay, that's nice. So now I would like to save the animation. So I can click save animation, and you can save it with the sequence of images, which you can post-process then by any script or any video software and so on to connect them, or you can go directly for AVI files. So my anim, okay. Here you can see you can set the image resolution, which is the actual one. So I will keep it here, and you can see how many frames per second. So if I take here, so one frame will take 1 second of the real time. But I would like to have it quicker, let's say, so because I have only 44 frames. So I set, for example, 5 frames, so far 5 time steps per 1 second of the video. So I will click OK. Now all the screenshots are generating and putting together to create the animation. Okay, and at the end I can go, yeah, here's my animation, and I can open it, for example, in VLC, and this is what this is what we get. And in this case, you can generate what you want. Even you can generate these views as well for non-transient simulation. So you can just go around your object to make nice animation. Okay, and last thing I would like to show you, for example, here is a special tool which is called Find Data, which can be used to analyze or to find any range of the data in your simulation or in your geometry. So I will take the case form, yeah, which holds my data, and I would like to see, for example, the magnitude of the velocity, which is, I don't know, which is, for example, larger than, how many, 20 meters per second, for example. So I will run the selection query, and now it picked me up only the values, only the cells which has the velocity larger than 20 magnitude, velocity magnitude, of course. And I would like to now click extract selection to really just see only the selected part. Okay. Right. All right, maybe it's okay, I guess, but I need to get rid of, sorry, it was okay. So I create 3 selection, but I didn't click apply. Yeah, so this is what I wanted to get. So now I have only the selection. I can, for example, visualize the full geometry, surface with, or just a wireframe. I can get rid of the selection by clicking this icon. I can go for opacity lower and visualize it, for example, just as the black lines. And now I can, for example, go for, again, the velocity, just to see really that there are only the values larger than 25. And for example, I can run again my simulation to see what is happening during the simulation, to see only the, let's say, the cells with the velocity higher than 20. Yeah, and in this case, you can play really in different ways. You can combine any filters you want and so on. Okay, so just quickly, and so I will show you some additional tools how to create. For example, this mapping results on input geometry is pretty cool stuff. So I will quickly show you this. So Drifter case, which I have prepared here. Yeah, computed Drifter, and I will directly open the geometry. Okay, and okay, I will close this one. I will close this. Not close, I will open it, of course. So what I would like to do now is, for example, to visualize the surface streamlines on my car body. Yeah, because on the car body there is just a velocity 0, so there is nothing to visualize. So ParaView provides you option how to sample the resulting fields or on any object. So I can, for example, I can open my original STL of the car body, so which is here, and I don't know the name, so I can read it here. So 01 body closed, so which is 01 body closed here, and state body and state windows, and last is mirror cover. Mirror cover is here. Okay, so I will open it. So I will open all these files. Now you can see, because the input geometry was in millimeters, right? So I need to scale it. So first you can group any items here in one group, which you can refer to. So this is this option, group datasets. I will create this group datasets. So car STL, let's say. I can name it by double click, right? You can change the name of any item here. Then I will apply the transform tool, so alphabetical and transform, which is here, and I will scale it to meters. Yeah, so scale factor 0.001. Okay, now I can zoom again, go inside my mesh. Again, sorry, Now I move the box. Where there is it? Okay, this was not my intention. So again, okay, zoom. I will go out for this show box, but otherwise it is interactive and you can accidentally touch it. Okay, so this is my input geometry. Just to visualize, I will visualize the solid to see everything is in white. Everything should be in white. All right. Okay, okay. All right, and just the color. All right. And I would like to map the results on this body. So I would like to scale it a little bit, yeah, to have the intersection with the internal faces to be able to create a map. So I will enlarge a bit this body. Okay, and now I can use this sample remap, or what is the called? Resample with datasets. Yeah, so this filter resample with datasets. Now you say what is input. So input is my data, so the whole data, whole internal field, and the source will be my transform. So this a bit extended input geometry. So now it computes the intersection with the internal field and maps the values on the STL body, on the STL geometry. And after that, we can be able to visualize both velocity and any other field on this STL body. So on the original shape of your geometry, not the meshed shape, for example. Okay, so here we have it. And now, for example, I can visualize the velocity and go for surface LIC filter, which shows you the surface streamlines. And if you go a little bit bottom, you can enhance the color. So I like the combination of multiply and enhance control color only. Perfect. And for example, to streamlines, I can visualize, okay, what I did. Oh, I can, for example, visualize the pressure, static pressure on the body. Yeah, in this way. Additionally, I can play around again with the streamlines and so on. So this is how to manage it. Pressure contours. Okay, so the last thing, how to create the pressure contours. So I can go back for surface, let's say. I would like to see the pressure contours on this body, right? So I can visualize the color legend, and I can here discretize the values. So I would like to see just the 20 values. I can also go to rescale my color range. So I will go from -1000 to, let's say, 800 to see also some blue color. And now I can apply the contour. So the contour will create the contours, so the pressure contour with the value set here. But I would like to have the full range, yeah, which follows my pressure legenda. So maybe it will be better to show you this again. So yeah, so I will go for contours, create a contour range from -1000 to 800, and I have created 20 colors, so I need to create 21 contours to fit my discretization of the color map. Now I can visualize it, for example, as wireframe, and I can go for wider lines, and yeah, basically this is it, for example, and color it as a solid. to be black, for example. Yeah, so this is the pressure contours, and I can also visualize it with the streamlines on the surface, which could be maybe interesting. Okay, so this, for example, this we have. Yeah, so in this way you can play around. You can, for example, create another slice here on the internal mesh. So I will create, let's say, this is y-axis, right? So I will create a slice in the middle. I'll close this. Yeah, to see pressure contours also here, or the velocity with the bake area and so on. So you can combine what you want. You can visualize as a wireframe. Yeah, so any options are available. Okay, and the last thing, maybe I'm really late. So ParaView provide also the batch scripting mode. So there are two executables, PV-Python and PV-Batch. So both are Python interpreters that runs ParaView's Python script. So Python can be managed by Python scripts. It uses the Qt library. So any item, any function from Qt can be called from these Python scripts. And additionally, PV-Batch is basically the same, but it is designed for batch processing and can be run in parallel. Yeah, so it can be run on the clusters, for example, which PV-Python can't. And ParaView, because I can start to explain any function which can be called. So ParaView offers to record what you do and generate a Python script automatically. And the script then can be called from batch automatically. So I will go quickly to show you some super easy example. Let's say, okay, I will open again. So I will close this because I'm scared of my memory. Not the computer's memory. And okay, I need to start from very beginning. So when you would like to record what you are doing, then you need to go for start trace here. So start trace and okay. And now ParaView is tracing any movement I will do. So first of all, I need to load the case. So I will just, for example, visualize the body with this, okay, with this pressure distribution. So I can, for example, change, just to show you, I will make it, okay, grayscale, let's say. And this I would like to, okay, this is, and I would like to save a screenshot of this. So I will save a screenshot, my image, let's say, yeah, with this resolution, okay, and that's all. So I will click on stop trace. Now I can see the script, so I can save it. So save, and to my working directory. So computed drift evening test. This was my case, my script, let's say. So my script is saved now. So basically, this is my image which I have generated. So I will delete it. So no image is here, but here's my script. So I can go to the command line and call this PV-Batch. So, and you can find it in TCFD installation directory inside the bin folder, and there is PV-Batch exe, and the input will be my script. So hope I create it in a correct way. So now I run the script, which basically do on the background what I have just done in the ParaView. Okay, just cannot render this render view, and if I click it, all right, I see nicely automatically generated image. Okay, for example, the legend is not nice, so I can go, for example, to script and manually change whatever I want. So for example, I would like to see larger resolution, let's say 2040 and 2200. Oh, and I need to save it, of course. Save. and I can generate it again, and this will be the last point to mention or to show that by this script you can generate it. Then you will quickly get familiar with the commands. You can change them and you can incorporate them in your workflow. So any design can create the same visualization just by script and not clicking in the ParaView again and again. Okay, just check if the resolution is higher. Yes, it is. So I think I'm too late, and basically I'm at the end. So I don't know if Luboš is sleeping. So Luboš, are you there?
No. I'm still here. It was pretty impressive, Radek. Thank you for it. So I'll take back
Yes.
the presentation. I will hopefully stay here because we had some technical problems. So let's see if it works. Can you see my screen now?
Yes,
Okay, so this.
Yeah, the
Okay,
Spitfire I can see. Yeah.
Okay, thank you. So this was Radek's live example of ParaView. I believe there was a lot of what was shown. So right now I would like to ask the audience for the questions. So feel free to ask questions. We will answer a few of them right away, and the rest will be answered later via email. Yeah, we have so far we already have a few questions. It was more or less questions about the availability of the recording of this webinar, so you can be sure we will make it available on our YouTube channel. Also, you can get it there through our website, and we will also send to all of you the recording. So you can be sure you will be able to see it again, and if you are interested in some particular feature, you can see it in the recording again, or of course anytime you can contact us. Radek, can you see any question? I can see any question which was not answered yet.
Right.
So maybe
me neither. I can't see any question.
Okay.
So
Okay. So let's conclude. We are pretty long anyway.
yeah, right.
So yeah. So yeah, we would like to thank you for your attention. Stay tuned. Feel free to contact us anytime. It's our job and also a pleasure to support you. So feel free to get in touch with us. We will gladly answer all your questions and comments.